Okay, so we're going to talk about zero-sum games. We're going to go over the simplex algorithm. You're going to show you how to actually do the computations. And then we're going to show you that linear programs, we've noticed something about linear programs is they can be used in a lot of places. And we're going to show to some extent why this is. Okay? So, so remember a two-person zero-sum game. Okay, for a mixed strategy. Okay, so each of the players, there's two players. One player has M strategies available to him, and one player has N strategies available to her. Okay, so that's what. So the payoff is you get a payoff matrix. If he plays strategy I, if he plays play I, and she plays play J, the payoff is G of IJ. It's this matrix. It's in this matrix, okay? So for a mixed strategy, instead of me saying I'm going to play a row, I'm not going to play the same row every time. It says I can play any of my distribution over my strategies. I play a probability distribution. So if it's a probability distribution, what do these xi's add up to? 1, right? Okay, so that's the main thing about probability distributions is there are a bunch of numbers, a bunch of probabilities that add up to 1, and they're usually not negative. Okay, so so a column mixed strategy. So the column player is a she in this particular exposition, and so the column player can also play a distribution, right? So you can remember the game we used as an example is rock, paper, scissors, right? You're not going to play rock every time, because then I would play paper every time, right? What you're going to do is play a mixed strategy. You're going to play 1/3 rock, 1/3 paper, 1/3 scissors. You can tell me you're playing that. It doesn't really help me, right? Does that make sense? Okay, so the payoff for the strategy pair. Now these are no longer, you can't just look up the payoff in this matrix. You actually have to calculate what this means. So we calculate it using expectation. We say the probability the expectation, the value of this game is just xt transpose times g times y. Okay, it's just this matrix product. Okay, so it comes from which is also this particular expression. Okay, it's just expected value. If I play x, if I play from my distribution x and you play from your distribution y, the probability that we play ij is xi times yj. So it's xi times yj times gij. That's what this thing will give you, right? Because we're independent. We're assuming that the mixed strategies are playing independently. Because otherwise, it's not fair. If I see what you play, it's not really. That's not the way the games are. Okay. Okay. So recall now in this case, what we're thinking of is the row is minimizing and the column is maximizing. Okay. So there's a single entry in there. The payoff is that entry. If that entry is 5, that means the row pays the column 5. If it's -5, it means the column pays the row 5. Okay? Or the row gets 5 from the column. Okay, so just to remember what two-person zero-sum games were. Okay, so now let's think about what the best response defense is. Okay, so the row goes first. Okay, so let's play rock, paper, scissors. Hey, Alex. Hey, Alex, get off the phone, man. Let's play rock, paper, scissors. Okay, you go first. Oh, no, that's not what I meant. Okay, so, okay, now ask me to go first. Play rock, paper, scissors. Okay, I'm going to play 1/3, 1/3, 1/3. That's what going first means. Okay, that's what it means. It's very important that you know what going first means. It doesn't mean I make the play. It means I announce my strategy. Okay? And when I announced my strategy, Alex was stuck. right? There was this thing where, okay, well, he couldn't really do much once even though I announced, though I told him he could do anything he wants. He could always play rock. He could play scissors. He's not telling me anything about what he's going to do. I'm telling him what I'm going to do, at least in terms of this probability distribution. That's what it means to go first when we talk about this, right? It doesn't mean I play rock, okay? It doesn't mean I choose from the distribution. It means I announce my distribution, okay? Okay. You can go back to the phone, I'm sorry. Okay, so now I'm playing first. So now the row plays first. What I'm going to try to do is I'm going to find a row. So X goes first. He plays as X, and now Y gets to choose. Right? Y gets to do whatever he wants, or whatever she wants. Okay? X is the... So here, who's going first? Right. Okay, so this is right, except this should be, here, just a second, let me see this. Let's try that. Okay. It worked better before. Okay. Why? How's that? Okay, why? That's good. Okay, so you're trying to find a Y. Okay, so these things should be a little switch. What you're trying to do is you're trying to find a Y. Row goes first, where the best column, I see, okay. Okay, so the best column is not too low. Okay? So you're trying to find a distribution over the rows. You're trying to find X, where no matter what Y does, no matter what Y does, you don't do too badly. Okay? So example, what's the value of R? Okay, so what we're trying to do is we're trying to pick the X's to maximize. I see. Okay. I think I switched it around. I'm sorry. So here the column player is minimizing, the row player is maximizing. That's what my issue is. Okay. So what I'm doing is the column player is minimizing, and the row player is maximizing. Okay. Okay. So now what this row player is trying to do is get the biggest numbers here as possible. So he'd really like to play paper, and he'd really like for the column to play rock. Okay, so he's trying to maximize. So pick X1, X2, X3 to maximize the payoff. So how would you do that? How would you pick X1, X2, X3 to maximize the payoff? Now, remember, the column can play any one of these. Okay? He knows our strategy. So, in fact, what's one of the strategies he can do? He can play this column, right? So we want to make sure that whatever he gets from this column is we still get a good value from this column. What does the column player get from this column? 0 times x1, 1 times x2, minus 1 times x3. Okay? That's what the column player gets from playing this column. What does he get from playing this column? Negative x1, 0 times x2, positive x3. And what does the column player get from playing this column? x1 minus x2. So what we want to do is we want to pick our x1s to maximize whatever the column player responds with. Okay? We want to maximize, we know what he gets here, we know what he gets here, we know what he gets here. Any linear combination of these is not going to be any better than any one of these. Okay? So we want to pick our x1 to make the responses for the column be as bad as possible. Okay, so what are the responses? This is one response. It's x2 minus x3. This is one response, negative x1 plus x3. That's the value he'll get. And it's x1 minus x2 is the value he'll get. Okay? So I want to figure out what my xi's are to maximize the column's, maximize my payoff. And my payoff is basically some linear combination of the columns payoff. And the column gets to go second. So I want to make sure every one of these, he has no good response. So I want all of these guys to be large. That's what the min is here. Okay? Okay, so I want to maximize this. I want to pick x1, x2, x3. And how might I do that? Yeah, I think you guys maybe should be on the homework here. It's, so what we want is we want a linear program where you minimize that. So the value is going to be z is going to be the min of those three variables, right? So we say the value has to be less than or equal to x2 minus x3. The value has to be less than or equal to negative x1 plus x3. And the value z has to be less than or equal to x1 minus x2. That's how you write a min with a linear program. Okay, now you're trying to make that min as large as possible. You want to make every one of the columns' response as good as possible for you, which is maximizing. Okay, so then you maximize z. And then you have to have a probability distribution, so that's x1 plus x2 equals 1. So that's a linear program. So I could find my optimal mixed strategy using a linear program. Okay, now in standard form, generally you have all variables on this side and the constants on this side. So I just put it in that form. I subtracted the z's, I made it greater than, and it's a max. What? This is x2 minus x3 minus z. Is he greater than 0? I just solved this. Oh, plus x3. This should be plus x3. You're right. Sorry. Okay. Okay, so now computing the best defense. The column goes first, so you do the same thing. Rochambeau. So here, y is going first now. Okay? So y has to announce his mixed strategy. So he's trying to pick his y1, y2, y3 so that it's as bad as possible for the row, or as good as possible for him. And he's trying to minimize. The column player here is minimizing. So he wants to make the max, the worst possible response. For this is a row can choose to do this, the row can choose to do this, the row can choose to do this. So whichever one is worse for him, he wants to minimize that. Okay? So again, you could write down a linear program. It should be y1 plus y2 plus y3 equals 1. But you could rewrite the linear program. This should also be plus y3. Okay? So now let's write down both of these linear programs. Okay? So these are just the linear programs. I said where the column, I announce my first strategy, then Alex gets to do what he wants. He announces his strategy, and I get to do what I want. Okay, when I announce my strategy and he gets to do what he wants, who has the advantage? If I announce my strategy and he gets to do whatever he wants, who gets the advantage? He does. Well, if he announces his strategy and I get to do whatever I want, who gets the advantage? Okay, so you would think, this one, the row announces his strategy, and now the column gets to do whatever he wants. So the row is trying to maximize, but this says the column is trying to minimize. So z should be, here the column has the advantage, right? And so z is the value the column gets. So z should be less than w. Right here the row has the advantage, and the row is trying to maximize. So w should always be bigger than z, because here row has the advantage, so clearly w can't be worse than when the column has the advantage. Okay? Okay, so the column defense LP is an upper bound on the row defense LP. Are they linear programming duals? They are. Okay, so z is equal to w. So it doesn't matter who goes first, right? I can announce my strategy, or you can announce your strategy. It doesn't matter. Or we could both announce our strategies. If we're both playing optimally, the values are the same, right? Yeah. 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 Right. So that's right. What he said is I could tell you, I could say I'm playing 1/3, 1/3, 1/3, and he's not gonna get any advantage out of that. Okay. But why doesn't he only play rock? Why does he actually do something different than just always playing rock? Because his value for rock or paper or scissors are all the same. Why won't he just play rock? In real life, why wouldn't you just play rock? Because then I would change my strategy to paper, right? So he's going to play 1/3, 1/3, 1/3. To both, he's going to get the same value by playing 1/3, 1/3, 1/3, and he's going to keep me from changing my strategy to get a better value. Okay? So this pair of strategies are an equilibrium strategy. They tell you, if you play 1/3, 1/3, 1/3, and I play 1/3, 1/3, 1/3, neither of us have an incentive to change our strategies. They're both optimal. Nothing I can do to get any better value, and nothing you can do to get any better value. Okay? So the fact that these things exist is a bit shocking. Why is it true that if I see your strategy, I can't change my strategy to something else and do better? Right? This is a rather amazing thing, and with linear programming duality, it actually just follows from linear programming duality. Okay? So I think it's amazing, right? That's a lot of amazings. But this is von Neumann's minimax theorem. He proved it without the concept of linear programming when he first proved it. But around then, Dancing came up with these concepts of linear programming as well. So it says the row goes first is equal to the value of the column going first. Right? It says you could always play this game. Okay? So who's heard of Nash's theorem? Who's heard of Nash's theorem? Okay, so this is sort of a weak version of Nash's theorem. Remember the game I described, Prisoner's Dilemma, where you can either knock out your buddy or not. So that's not a zero-sum game, right? The matrix there, different people got different payoffs in the matrix. So that's a more general setting. The same statement is true that there exists an equilibrium, but finding that solution is hard. I mean, nobody knows how to do it. Here, with zero-sum games, where player one pays player two, or player two pays player one, for each outcome, nobody benefits, right? The sum of the two payoffs is equal to 0. That's what it means. In that case, you can actually find the solution using linear programming. Okay. Okay, so in the slides from lecture 19, I do a version of this for a game that's not so simple as rock, paper, scissors. It has an extra strategy where the actual optimal strategies are kind of hard to figure out. Okay, so you actually need the power of the linear program. Rock, paper, scissors is a little easy, right? We can immediately see what the optimal solutions are. Okay, but in general, this is not true. Okay, so so now we're going to go to the simplex algorithm. We're going to go over and review the simplex algorithm, and then we're going to go into more detail and cover how it works. Okay? So remember the simplex algorithm. You start at a vertex of your feasible region. You move to a better neighboring vertex until no better neighboring vertex. So here's my system of equations. This is a picture of the feasible region. The variables have to be positive, which means that they have to be over here. Okay, and each one of these is one of these constraints here. I guess this one is which constraint is this one? Just to get oriented. Which constraint is this one? Well, I think it's the first one, right? It's just the steepest slope. Okay, so this is a feasible region. So we start at a vertex. This is a vertex of the feasible region. What is a vertex? Do people know what a vertex is? So I have something highlighted in red on this slide, right? The equations here. Those equations what happens at a vertex is two of these inequalities hold with equality. Two of these constraints hold with equality. So at this point, x1 is equal to 0 and x2 equals 0. So it holds with equality. Okay? So that's what we mean the intersection of two constraints. We take this constraint, and we find the point that intersects. Right? Two lines intersect at a point. Okay? Does that make sense? Okay, so that's what a vertex is. It's abstractly, without a picture, so pretend the picture is not here, it's just the intersection of these two lines, x1 equals 0 and x2 equals 0. Okay? That's what the vertex is. Okay, in the picture, it's this point. Okay, so now we move to a neighboring vertex. What do you think the neighboring vertices are? Do people have an idea what the neighboring vertices of this one is? Would you think this is a neighboring vertex? Okay, so in the picture, it's very easy to see. It's either this one or it's this one. So in this abstract language, it means you take one of these constraints and you say, okay, well, this one doesn't need to be tight anymore. And then you make another constraint tight. Okay? So when I say tight, I mean set it equal to the right-hand side. Okay? So this one, I drop which constraint? For this particular vertex, which constraint do I drop? Which one? Yeah, this is x1. x1 equals 0. For that one, I drop the constraint that x2 equals 0. Okay, so this one is, those two constraints are tight. It's the intersection of those two lines. x1 equals 0, and 2x1 plus 10x2 is equal to 33. Okay? Yeah. I could have picked either one. Oh, instead of the other equation, yeah, okay. So how did I know? I don't know. He's asking, why didn't I pick this equation here? Okay? So what I'm going to show you a little bit more detail what to do. But really, what I'm doing is I'm relaxing the constraint that x2 is equal to 0. Okay? And then I'm just moving it up until I hit the first constraint that I violate. Okay? So that's how I'm going to do it. But he says, you know, I could drop this constraint and just throw in another constraint, and then I'll find a vertex that's not in the feasible region. What he's worried about is this. For this picture, you have this line, and this line, and this line, right? You have three constraints, including the non-zero constraints. So if I drop this constraint, he's worried that I'm gonna go to this point, which is not a vertex because it's not feasible. So what I'm suggesting is that when you drop this constraint that x2 equals 0, what that means is you're floating away from this constraint, right? And now you just go until you find the first constraint that you hit along this direction. Okay, and that by just this process of going till the first constraint that becomes tight makes you be at a vertex, right? Because all the other constraints remain satisfied, and this one, if you go any further, this one becomes unsatisfied. Okay, so that's how we chose to go there, and from there, is there a neighboring vertex that's better? The optimization function is x1 plus x2, so we're pointing in this direction, right? We're trying to get there. This blue line is just. This blue line here is the line that x1 plus x2 equals 0, equals our current value of our optimization function, right? And this is the direction of improvement, x1 plus x2. It gets bigger and bigger if you go in this direction. Does that make sense? Okay, so the blue line says x1 plus x2 equals whatever value is. All these values have the same value. They're contours, right? Like the contour map of a hill or something, right? So this tells you as you go up this way, these contours are there. Okay, so now it means that way you're still improving, right? x1 plus x2 goes up, so that vertex is better. And the particular inequalities that hold with equality at this point. Okay, and finally that's there. Okay, how do we know it's optimal? Again, the direction of improvement is this red direction. And now this blue line is this contour, right, that says all the points that have this value of x1 plus x2. Right? It's x1 plus x2 equals whatever this value is. Okay? And now, what do you know that which values have higher values of x1 plus x2? Points out here, right? Are there any feasible points here? No. Okay? Okay, so why is it optimal? Because if you draw this line corresponding to the objective value equals the current value, that's what this blue line is, the whole feasible region is on one side of it. Okay? Now, that wasn't true at the beginning, right? Here you drew this line where x1 plus x2 equals this value. The whole feasible, there was points in the feasible region. And in particular, two of the points in the feasible region are neighboring vertex. There's going to be a neighboring vertex in the feasible region, which you can go to, which is better. Okay? So that's why it's optimal. Entire feasible region is on the wrong side. Because all your neighboring vertices are on the wrong side, then you can tell the whole feasible region is on the wrong side. Okay? Okay, so, and that comes from the fact that linear programs are convex. They're convex bodies. Okay? Okay, so now that's fine. This is in 2 dimensions. The picture is nice. So how is it in 3 dimensions? Okay, so what's a vertex? Is it 2 tight constraints? Okay, so you guys are ahead of me. So I gave you an example of which point, right? Okay, so now you guys all know it's 3. It's the intersection of 3. But let me just go a little slower and show you why. Okay, so the reason is 2 constraints are 2 equations, right? You have 2 equations and how many variables? 3 variables. So it's not going to, from 2 equations and 3 variables, you can't really determine all the values, right? It becomes 3 unknowns and 2 equations. So it defines a subset of the points in that space, but it doesn't define a point. Okay, in particular, 2 equations and 3 unknowns defines a line. Okay? It doesn't define a point. So you need 3 equations and 3 unknowns to find the values of the unknowns, right? Okay. So 3 tight constraints define a vertex. Okay, so in n dimensions, how many constraints do you need? You have n variables, right? Because n dimension, each dimension corresponds to a variable. Okay, and n constraints define a vertex. Okay, so we're going from this sort of simple example to try to see how to write code that will implement this simplex algorithm. So, just some terminology. A constraint defines a hyperplane. In 2 dimensions, it's a line. It's just a constraint, x plus y equals 5. That's x1 plus x2 equals 5. That's a line. That's an equation of a line. Okay? In 3 dimensions, x1 plus x2 plus x3 equals 1 is a plane. Okay? And in n dimensions, we just say, it's called a hyperplane, but it's just a generalization of a plane. In n dimensions, the vertex is the intersection of n hyperplanes. So this is just another terminology. N constraints define a vertex, or n hyperplanes, and the definition of the hyperplanes come from your constraints. Okay? Okay, so there's 2 tasks in the simplex algorithm. What are the 2 tasks in any algorithm? Well, the first task in any algorithm is see if you're done. If you're done, you want to stop and output the answer, right? And if you're not done, then you want to see what to do next. Okay, so these are not very, very complicated. So let's think about a generic LP. Like, it's not a 2-dimensional LP. This is an n-dimensional LP. The dimension of this is the number of variables. Okay, so when I talk about dimension, it really is just the number of variables here. Okay, so now the simplex algorithm, what we're going to do is we're going to pretend we're in this situation where the origin is feasible. It may not always be true, but let's just assume that's the case here. So the origin is feasible. Okay, so now the origin is feasible. The origin is a vertex. It's the intersection of n constraints, right? Because there's n variables, x1 through xn. So it's the intersection of these n constraints, and that defines that point. So it is a vertex solution. There's n constraints that hold with equality. Okay? Now, is this optimal? How do we tell if this is optimal? Is there an easy way to tell if the origin is optimal? You could check all the neighboring vertices, but there's an easier way, and this is a very simple example. That's right. That's what we want to do, but we're not even simpler than that. We're gonna make it. Neighboring vertices is complicated because now we have to figure out what neighboring vertices are and all these things, right? So what we're going to do is do something that's really stupid at this point. Just by inspection. Okay. Okay. So think about he's got an idea. So one idea is look at C. Look at your vector C. Okay? Your vector C is C1 times this objective function is C1 times x1 plus C2 times x2 plus C3 times x3, right? What if all of those are negative? If all those CIs are negative, is the origin optimal? Does everybody see that? That if all the CIs are negative, we're at an optimal vertex. Okay, so when you're at the origin, it's actually quite easy to tell if you're optimal. You just check whether all the CIs are negative. Okay? If all the CIs are less than or equal to 0, increasing any xi decreases the value of this objective function. So making any one of these equalities not tight and allowing xi to get bigger than 0 is only going to decrease your value of your objective function. And decreasing is bad. You don't want to decrease it. You're trying to maximize, right? And so that's you know you're done here. So you're optimal. This is always good to know when you're done in a rather easy mechanical way. You just check each entry of the CIs and see if they're positive or negative. Okay? If there is a CI that's greater than 0, what should you do? Yeah, where to go next? Well, you find a CI that's greater than 0. For that xi, you just start increasing that value. You make that guy not tight. Okay? And how much do you increase it by? Yeah. Okay, so just in words, how much do you increase it by? How much do you think, what did we do here? Yeah, we just kept increasing this until it hit another constraint. Okay, so we increase it till the first tight constraint. And how do we find the first tight constraint? For each one of these constraints, we just plug in, right? We plug in the value, right? For this point, we plug in solve for xi where it becomes tight, right? For this constraint, all the other variables, the x1 through xn, are set. They're fixed. So you have an equation here that corresponds to this line. You have all the values except for this new variable. It's free. And you figure out where it's tight, and you do that for all the constraints, and you pick the smallest one. Okay? You can increase xi. It's not optimal. So we're done with that. We can tell whether something's optimal or not, but we can actually, we want to see where to go next. There's a positive SCI, so we can increase xi. Okay, so now if xi is greater than 0, is no longer tight, so you go until you hit another constraint. Okay, and the way to find those constraints is pretty easy, right? Because all the values are set at the origin, all the xi's. You know them all except for the one you're changing. And so for each one of the constraints, it's an equation with all these n variables. N minus 1 of them are fixed. So you could solve for the xi at which it becomes tight, and you just pick the smallest one, the smallest xi. Okay? Yeah. Yeah, good question. We'll come back to that. Okay. He's worried that the origin is not even feasible, for example. Okay. So what happens is we got rid of one tight constraint, and now we go until another constraint is tight. Something holds with equality. So we're at a new vertex. We get a picture like this. We go from here to here. So we used to have two tight constraints, and as we go up, we only have one tight constraint. And when we hit this one, we have two tight constraints again. So it's a vertex. And so the same picture holds. We drop one constraint. We have n minus 1 tight constraints. We move along the edge until we hit another constraint. We have n tight constraints. So we have n tight constraints. So you're at a vertex. Okay? So let's look at this example. So what we're going to do is we have this thing, is the origin. Okay, so again, at the origin, these two, 4 and 5 are tight. Okay? Inequalities 4 and 5 are tight. You drop the constraint that x2 equals 0, right? Because x2 has a positive value in the objective function, right? So we're going to increase x2 until what constraint becomes tight? Which one becomes tight? Can you see? X1 is 0, right? So x1 is all 0. So you have these three constraints become x2 is less than or equal to 3, 2 times x2 is less than or equal to 9, and x2 is less than or equal to 4. So the tightest one is that x2 is less than or equal to 3, right? So the third equation is going to be the new tight inequality. Inequality 3 becomes tight. Tight constraints 3 and 4. You have a new vertex, 0 and 3. Okay, the x1 value is 0, the x2 value is 3, and the value of the objective function is no longer 0, it's 15. Okay? Okay, so this is easy. If you're at the origin, life is easy. You could both tell whether you're optimal. You just check your CIs, and you can go to the next vertex quite easily. Okay, so these two things that we need to do are really easy. But now where are we? Are we at the origin anymore? No. Okay, so this is like a disaster. Okay, so I just assumed, and when you assume, you put an ASS before a U and a ME, and so okay, sorry. So now what? So we're not at the origin anymore. I saw that it's a corny 1950s joke. Okay, sorry. You get an ass before you and me. Okay, sorry. Okay, so we do it a lot in this class, so don't think of that joke every time I say assume. That would be a disaster. Okay, so now what we're gonna do is this was really beautiful in this picture where you had x1 and x2, being at the origin of this system. So what we're going to do is we're going to translate the coordinate space so that our new point is going to be the origin of a new coordinate system. Okay? That's what we're going to do. That's how we're going to implement this. We're going to make a new coordinate system where our vertex now is going to be the origin of this vertex system. And what is it? How do we do that? So say we're tight with these two constraints. Okay? So we're at that vertex. We're at the point in the middle. Okay? So now the coordinate system we're going to use is the distance from each constraint. Okay? If you have n constraints, you have a distance from each constraint. That's each one of your coordinates. Okay? So where the vertex itself is at the origin, right? It's at distance 0 from all the constraints. Okay? So in this new coordinate system where you define a point, the coordinate of this point x is the distance from constraint 1, comma, the distance from constraint 2. Okay, this is a new coordinate system. You can now define any point in your space as the distances from these two constraints, and that will give you a coordinate, for a way to represent that point. Okay, so yi is the distance from constraint I. So this at point x is in this new coordinate system is the point y1, y2. Yeah. No, you could have if you have m equations and n n variables. No, no, no. No, you have, in n dimensions, in n dimensions, say you have m equations, okay, many more than n, which is always the case, okay, and you have n, you're in n dimensions, so you need n of them to define a point, not the intersection of two of them. The intersection of two of them is going to be some sort of hyperplane or hyperline. No, m choose n is not typically polynomial. So if you take m to be 2n, twice as many equations, it's exponential. So, right. So what he's asking is how many possible intersections of these systems are there? And that's a good point, actually. So there's m equations, n unknowns. So you need a subset of n of these to define your unknowns, right? So how many ways are there to choose n equations from m unknowns? So there's m choose n, okay? So if m is, say, 2 to the 2n, let's say this is 2n, choose n, this is a big number, right? This is, by Stirling's formula, this is right, it's exponential. Does everybody know Stirling's formula? Okay, that'll be on the test, okay? Okay, so that, but anyway, that's a big number, right? So at this point you're, I mean, on the one hand, it's a fine number, right? Because it's finite, right? It's not an infinite, in terms of n, it's finite. A priori, for linear programs, you have real numbers, right? These have real values. So this is already a brilliant bound in some sense, right? It's not infinite, it's finite, but it's not, it's still big, okay? If you have very few variables, it works, right? Okay, so yeah, okay. So now, how do we? This is a little scary, right? Now you have to redefine everything in terms of this new coordinate system. Okay, so this is like, oh, how do I compute my distance from this constraint? This is not too bad. This is just, you just multiply a times x, and then you subtract it from bi. That is your distance from this constraint. It's not very hard to compute it, right? You just compute a times x, and then you see what the value of that is, and compare it to b. Do you see that constraint 2? Is some vector times, it's a set of points where a times x equals b. Okay, so now the distance away from it is where a times x does not equal to b. And however much that it does not equal b, that's your distance away from that constraint. Okay, so it's actually reasonably straightforward to find this new coordinate system, to compute the yi's from the x's, from the old coordinate system. Okay, so that's an easy process to actually write out coordinates, the new coordinates, given the old coordinates. Okay? Right? It's just a nice linear equation, nice linear relationship. Okay, so recall that for origin, xi was the distance from the constraint xi greater than 0. So by analogy, now what we've done is, at the origin, all the xi's were just the distances from the 0 constraints. So now in this new thing, the yi's are distances from our tight constraints. So it's exactly the same situation. Once again, we're at the origin in this new system. Okay, so we're basically at the origin in the new coordinate system. So then we could do our old algorithm. The one thing we need to do is we need to rewrite the linear program in terms of this new system. Right? We have these new set of variables. We no longer want to use the xi's, right? Our old system was a c times x. We want to get it all in terms of yi's. So how can we do that? Okay, so what we need to do is we want to plug into the old system, right? What we need to do is get the xi's in terms of the yi's. We know the yi's in terms of the xi's. So now we put the xi's in terms of the yi's and plug back the expressions with yi's back into the old linear program. And now you'll have a linear program in terms of the yi's. Okay, so that's solving a system of linear equations, which is no fun, but we know how to do it. Okay? So for example, we have this tight constraint here, right? We went from 4 and 5 being tight to 3 and 4 being tight. So our new coordinates are y1 equals x1. That didn't change, right? That's the same coordinate as before, the distance from the x equals 0, x1 equals 0. Okay, and the new constraint is this constraint 3, which gives you y2 equals 3 plus x1 minus x2. Okay? Okay, so those are our y2's. So now what we need to do is solve for the xi's in terms of the yi's. Okay, so that for x1 it's easy. x1 is equal to y1. And x2 it's not. In this case it wasn't so hard to solve the system, right? It's pretty small. Okay, so now you plug in. Now you plug in wherever you had x1 there, you put y1. Wherever you had x2 there, you put in 3 times minus y2 plus y1. So let's just do this for the objective function. So remember, the objective function is max of 2x1 plus 5x2. So we plug in for x1, y1, plug in here, and we simplify. So that's our new objective function. Okay? In terms of our new coordinate system. Okay? Is that clear? Okay, so now, so we want to, okay, so that's, I just copied the objective function, but I did the same thing for all the others. That wherever there was an x1, I put in x1, I solved it, massaged it, I copied it out of the book, and this is what you get. Okay? Okay, so this is a new equation. Now, which ones are the tight equations here? The tight inequalities? Yeah, 3 and 4. They'll always have that form. They'll be the ones where the variables of interest are equal to 0, right? Because we're in the coordinate system. The coordinate system we're using is the ones where the yi's are all 0, right? That's what we're doing. We're making our vertex be at 0. So that means all the constraints, we will get constraints of the form y1 through yn are greater than or equal to 0, and those will be the tight ones. Okay? Okay, so they're sort of positive. Now they're positive just like the x's. We improve by increasing y1. Now we're in the same boat as we were at the beginning of when we assumed it was at the origin. Okay? So the tight constraint is going to be 1. So we improve by, now let's do this improvement by y1. Which one is going to be the tight constraint? We're going to increase y1. Why do we want to increase y1? Because the multiplier of y2 was negative, right? We're trying to maximize. So we want to increase y1. Okay? So how much can we increase y1? Well, the first equation says y1 plus y2 is less than or equal to 7. y2 is 0, so y1 it reduces to y1 is less than or equal to 7. 3y1 is less than or equal to 3. So that's, and this one is fine, negative y1. Increasing y1 only makes this one more satisfied. Okay? So tight constraint, I guess, is 2 on this one. The tight constraint should be 3 and 2. Okay? And the value there is 22. Okay? So now let's review this simplex algorithm. Okay, so in each step, we write the LP in the coordinate system from tight constraints. We check if it's optimal. How do we check if it's optimal? We check our new objective function and see if all the multipliers are negative. Okay, if they're negative, it's optimal. Okay, does objective function have non-negative multiplier? So in this case, it was 15 plus 7, y1 minus 5, y2. So no. So then you go to a tight constraint along some coordinate that improves. Okay, and that one is the tight constraint that we should have got. Okay? So we could set y1 to 1. Now we have a new set of new coordinate system, and we need to express the LP in the new coordinate system for the new tight constraints. Okay, and you can see this in the book. Okay, I use the book example on purpose so that you do it there too. Okay, and then you repeat. Okay, so this is the simplex algorithm. Okay, yeah. Yeah, you can pick. Do both, or anyone is going to be bigger. There's some subtleties which I'll cover after the break. So there are some subtleties there. I mean, you can always choose the biggest one, right? Or you can choose the one that has the biggest benefit. No, you have to go to another one and another one and another one, right? Right. You have to keep going. This is just one step. How do you go from vertex to vertex? Okay. But there's no argument. I made no claims about how many vertices I have to see, right? Because in that first example, I saw 4. Now, that was an easy example. There were only 5 examples. It was what he was saying. He's like, oh, there's not even that many vertices. In real polytopes, the number of vertices is huge. So there's nothing to say we don't visit every one. Yeah, we'll discuss it after. I'll give you a break, and then we'll discuss it more. Okay, so let me give you a break. Okay, so let me get your attention again. So the linear programming was invented in the West. Often these things happen in Russia and in the West. There was a time when we didn't get along, and so they weren't always shared. So it was invented in the West by a guy named advanced and reinvented by this gentleman named Danzig, who started the IEOR department here, and then he went to some place which we would rather not name. He's famous for linear programming. He's also famous for this story where he walked in late to class. He saw the homework written on the board, and then he went home and he solved the homework, and then he came back and the professor says, no, those were open questions. And so he had solved these problems that were open. And, well, he's like, these were really hard. And so that's Danzig, and so he's a rather impressive character. And so then it was also invented by this gentleman named Kantorovich, who was trying to figure out how to optimize the plywood industry in Russia. And so he came up with this notion of linear programming there as well. Kantorovich is also famous there's in the siege of Leningrad, the Germans had the city under siege. That's why it was called the siege of Leningrad. And it was really quite terrible. These people were starving, and although they're Russians, they're used to it. And so Russians are way tougher than normal human beings. So there's at some point the winter comes, and the Russians are actually happy about it. And so because this big lake would freeze, and across the lake they ferried in supplies to the city. Somehow the Germans had not cut off the lake. And he computed the ice thickness and made sure that the cars were driving the proper distance apart to make sure that, nothing bad happened. So, and so anyway, this is, that's Kantorovich. And so, okay, so we go on? Okay. Okay, so I read an article about Russians. Russians fascinate me because they're so foreign to me. Okay, so this in the 90s or something, the New York Times is talking about these Russian guys. They're in this godforsaken place, a northern city, that sometimes the ice melts, so ships go over the North Pole there, and it's really an industrial city. And they're talking to these guys, a human interest story. These guys are out there ice fishing. So I don't know, if you're from the East Coast, ice fishing in Maine or something, you have a cabin, you sit in there, you have a stove, you have maybe a little bit of liquor, maybe a lot of liquor, and and you hang out with your buddies, right? So in Russia, the lake or the river is dotted with these guys, single people next to a hole with like essentially garbage bags over them to protect them from the bitter winter. And so the New York Times article writer goes out to one of them and says, "Do you ever catch anything?" And it's, not really. Can you eat it? No, everything's polluted. When you catch something, what are they like? Oh, they're about this big. And it's like, well, why do you do it? It's what it means to be Russian. I just wow. I'm cold just thinking about it. That's horrible. Okay, so so getting started. Okay, so this is the review. This is how we do it. We start at the origin. We have this zero coordinate system. For each tight vertex, we can rewrite the linear program in that coordinate system. Okay, using essentially Gaussian elimination to rewrite the linear program. And so there's problems. What if the origin? Yeah. Oh, when you're optimal, right? As long you just keep going until you're optimal. So I didn't give you a bound on how long it would take. Okay. Okay. So what if origin is not feasible? What if the origin is not feasible? How do you find a feasible vertex? So the problem itself is, there might not be any feasible points, right? Optimization, you can also add the constraint that the objective value is at least something. Once you do that, that's the original linear programming problem. So feasibility is in some sense just as hard as all of linear programming, right? Feasibility with binary search. You have to throw in binary search to binary search for the optimum value. Okay, so it's a real question. So what you're asking, what is the feasibility question? You want to find an x where ax is less than or equal to b, and it's a vertex of this particular feasible region. Okay? So that's the question. How do you start? Okay, and so, what you do is you make a new linear program. Okay, so it's a self-reduction. So what you do is you introduce a positive variable zi for each inequality. That's how much you violate that inequality. That's what it means. So aix minus zi is less than or equal to bi. For any x, I could just set zi to be some value, bi, right? If I could set x to be all zeros and zi to be all bi's. And now these equations are definitely satisfied, or negative bi's. Okay? So with these positive variables, I can satisfy the equation. Okay? So now I want to maximize the sum of the negative zi's. And now I want to do so now this is a linear program. It just has more variables. It has the x variables and the z variables. It's just another linear program. But in this case, there is a vertex solution. Just the all zeros for x and whatever the violations are for z. Okay? So that is so once here, for this linear program, what we did is we wrote down a new linear program where we could find a vertex solution. And from that, we found the optimum. Now, the optimum of this linear program gives us a feasible point for the original linear program. And, this seems like a trick or a reduction. People actually have to really do this. So there's really two stages. When you solve a linear program, first you find a feasible vertex, and then you okay, so when there is a vertex solution, all these zi's are 0. If this value is 0, it means none of the inequalities are violated. So all the inequalities are satisfied, and x is a feasible vertex of ax less than or equal to b. Okay? Okay, so there's another problem. Is maybe a vertex. In this case, this box is the feasible region. And the constraints are there's a vertical line here, a horizontal line there, and y equals negative x here, plus c. Okay? So that particular vertex is the intersection of 3 inequalities, not just 2. So you could, this can cause problems, okay, because all neighboring vertices may be no better. It may be that there's a lot of these that are piling up, and you can think you can't move no matter what. Okay, so that's a problem. But if you sort of allow yourself to move no matter what, you can sort of go into a loop. So you have to be a little careful. There's two solutions. One is called this Bland's anticyclic rule, which is a particular method of choosing which constraint to put in. If there's ties, the problem is we can find the tightest constraint, but there may be many tightest constraints, and you have to break the ties among them. Okay, so that's or another thing you can do is for each equation. In real life, for max flow, you need things to be integer. But in real life, if you're given the data, your A matrix, which is your data, or your B vector, which is your right-hand side, those are data. It's somebody gave it to you. So just change it a little bit. Okay, so it's not going to hurt. Okay, because probably it's crap that came in. So, it's only approximate, right? Data is not that good, right? You go work with the real world. It's not that good. So once you can perturb it a little bit, and then you won't have this problem. Okay? Okay, so now there's another problem, is maybe your feasible region looks like this. Maybe one of your constraints is, it's positive. There's a constraint that says you're below that line and below the horizontal line. So what's the problem with this picture? Well, if the objective function goes this direction, you can just keep increasing the objective function forever and ever and ever. Okay? So that seems like a problem. It seems like maybe the simplex algorithm may not terminate. Right? And you can't just say because the region is unbounded doesn't mean there's a bounded solution. If the objective function went this way, the optimal solution would be that blue x. So even the region being unbounded by itself doesn't tell you there's not a bounded solution. So the simplex has to be able to do that. It has to tell you whether there's a bounded solution. It not only tells you whether or not the region is unbounded, it tells you whether there's an unbounded value. Okay? So what would the simplex algorithm do in this example? It would go from the origin, it would go up to that first vertex on the left, it would go over here, and now from there, in the blue case, it would just say it was optimal, because all the neighboring vertex this way, there's no benefit to moving, there's no benefit to moving that way. Okay? Moving that way actually is in the opposite direction from the blue line. So there's no benefit to moving that direction. And it says this, and there's no benefit to moving this direction. So therefore, this x is optimal if the optimization function is in the blue direction. If it's in the red direction, you're sitting at x. You look in this direction and say, damn, I can't improve in this direction. And you see that there's no tight constraints. You know that no constraints stop you from going forever. Okay? So once you see that, you just stop and say the value is unbounded. Okay, which probably means somebody input something incorrectly. Okay? So you can actually deal with that. Okay, so now let's look at the running time per step. Again, we haven't ever argued about how many steps. So checking optimality, that's easy. We just check each entry in the objective function. Okay, so now how do you find a tight constraint? There's order m constraints. You can't. Each one is at order n size. It can't take longer than order nm, right? Because you have the values of all the variables except for the one you're looking for, right? You're just trying to raise one yi, and so all you need you'll reduce those constraints to inequalities in terms of yi, and then you just write the tightest yi, right? If yi is less than 3 and yi is less than 2 and yi is greater than -4, the tightest constraint is that yi is less than 2. Okay. Okay. So now finding the new coordinate system. This is the fancy thing, right? So you started figuring out the yi's is easy. The yi is equal to bi minus aix. So that's easy to write the yi's. But now you need to rewrite the LP in terms of the yi's, which means you have to solve these equations for the x's in terms of the yi's, and that you can do. With Gaussian elimination. Okay? So this is just solving a system of equations. You did it in grade school. It's the same algorithm. Okay? Okay, so now that's a lot of time, n cubed, every time. That could be very large. So what you want to do is do it more efficiently. Now the system of equations here only changes by 1 right? Only one of the yi's change. All the other yi's are the same. So in fact, you can do it much faster. You can sort of do it in order nm time. Okay, so the total time of the update is only order nm. Is essentially the size of your matrix. Okay? Okay, so now how many steps? Now that's the question. How many steps are there before you get to the terminate? So in fact, people have engineered examples where the simplex algorithm will take an exponential number of steps to terminate. Okay, so this is a bit of a disaster. Okay, but it works. This is one of these rare, sort of an unusual case where it finds the right answer. When it terminates, it's right. And in practice, it terminates and it's fast. Okay, so why is that? Or, and that was sort of fine for a few years, but eventually, you know, as theorists, we could show you it working. I don't have time. I'll put code up that will show you the computation. Okay, it'll be on the web. Okay, so so now there's this. People wanted to get a polynomial time algorithms. So this was again the original framework and the simplex algorithm and this method was done a while before. It was not till 1979 that somebody came up with a polynomial time algorithm. Okay, so again, a Russian. They told us this time. And yeah, you should read the notes. It's kind of amusing as to what happened. So far, the ellipsoid method is not used in practice. The method was beautiful mathematically, and it really provides a lot of stuff. It's not implemented and used typically. Okay. Another algorithm was developed at Berkeley by Carmarker, and there what you do is instead of being on the boundary, you're somewhere in the middle, and you're moving toward the optimal. Okay, so that's why it's called an interior point method. So instead of always remaining on the boundary, his algorithm will do something like, you know, it's like, oh, I'm too close to the boundary. Oh, I'm too close to the boundary. Oh, now it wants to stay away from the edge. Okay? Oh, I'm about to go out. Okay, no. Okay, so that's what the interior point does. And you can work out the details yourself. So it's fast in practice. So the best codes these days are either interior point or simplex, depending on the problem. Okay? Some theoretical work said that on most problems, on smooth type problems, if you do this little perturbation that I was talking about, simplex is polynomial. You have to really have this almost degeneracy that makes it bad. Okay? Okay, so now we notice that linear programming solves I'm going to try to warm you up for NP completeness. Okay, we're going to use this notion of reduction. Remember putting out the fire, we hand it to somebody else and have it. So far, we do that, right? We say, oh, here's this problem. Let's write we could just write it as a linear program. No more algorithm design, right? You can just write down as a linear program. Okay? So why can we do that? Why is that coming out? Yeah. Yeah. Oh, it could be, the best solution could be on an edge, but there exists a vertex solution. Okay, that's what yeah. But I can show you. Okay. So how applicable is it? How widely applicable it is? So I have one more technical content. I may go a minute over, but try to stay in your seats. Okay, so circuit evaluation. So let's look at this. So we're going to say it's really, the reason, it's not an accident that we can use linear programming over and over again. We could essentially always use linear programming. Okay, that's what I'm going to show you to solve a problem. Okay? I mean, it's an existence proof. Nobody should do this, but this is an existence proof. Okay, say you have a circuit, and this is a circuit, right? That's what a circuit is. You have inputs that are 0, 1, or true, false, and, or, and not gates, right? That's what a circuit is. And now the circuit evaluation problem is just to evaluate the circuit, see what the output is. Right? Pretty easy. Okay? Okay, so now I'm going to say any circuit evaluation problem I could write down as a linear program. Okay, so what I'm going to do is I'm going to assign a variable for the value of each gate, x sub g. So they're clearly, we're going to model them as output of a gate, so they're probably going to be 0 and 1, right? 0 for false and 1 for true. Okay? And for these input gates, these are input gates, you just set xg to be 1 here, xg to be 0 here. And now we're going to write constraints for AND gates, OR gates. Okay, so now what should be the constraint for these OR gates? Well, one is that xg, the output value of this gate, should be at least, if either of the inputs is 1, it should be at least 1. Right? It should be true. If either of the inputs is true, it should be true. So that's those two. But if neither of the inputs is true, it should be false. So that says it should be at most the sum of these two. Okay? So that's how you code up an OR gate. And you can similarly code up an AND gate is xg can be at most the value of either of the inputs. Right? And AND says both of them have to be true for you to be true. So if each one is 1, you can be 1. If either one is 0, you can't be. You have to be 0. That's what this says. But if both are 1, then you should be at least 1. If both are 1 here, you get 1 plus 1 minus 1, you get 1. Okay? And for a NOT gate, you can do the obvious thing. So the output is 1 in a solution for the linear program if and only if the circuit evaluates to true. Okay? So you could write any circuit evaluation problem as a linear program. What? Well, the linear program itself will solve the integers in this case. Right? Because I proved it. I proved that if it has a true assignment, I'll get an integer assignment, which is true. Okay, this is what this argument says. I don't need to include it. It just happens to be true. Any solution is integral. Okay? So now the circuit value problem is completely general. Okay, it seems so simple to evaluate a circuit, but why is it completely general? Who knows why it's completely general? Yeah. Because of 61C, right? From circuits you build computers. From computers you write programs. The program is just a circuit, right? A computer program can be folded into a circuit. How? Well, it runs on a computer, so each level of the circuit is the computer, right? You just write down, it's a big circuit, it's not so pleasant, but you can do it. The number of levels is the number of steps your program runs. The circuit value problems models computation, all computation, okay? So linear programs can model essentially, efficiently, you could write down a polynomial-sized linear program if you have a polynomial time computation. Okay, that's why. Now, I would never do this. You don't want to write, this is not how you should code up things. But it tells you that, in some sense, if you try hard enough, the linear program can express what you're doing. Okay, next time.